Perfectly elastic collision. So this is a scheme of process of perfectly elastic collision, how we see it from the point of view of mechanics. There is a phase before collision. We can see a system of particles. So let's consider only two particles. There is a particle 1 with velocity v1 and second particle with velocity v2, where naturally v1 is greater than v2. Because of this, the particles gets into collision, or collision starts. The points touch each other in some time. So this is a start of the collision. There is a phase of process of actual collision where these particles, and we can consider them for this time, they are small bodies, are deformed, but they are deformed only in elastic way. So all deformation after collision is get back, and we get the same shape of each particle as it was before collision. And finally, from the collision, particles continue with new velocities, v1 with star and v2 with star. So m1, m2 are masses of particles, v1, v2 are velocities of particles before collision, and v1, v2 with stars are velocities of particles after collision. We need to find a relationship between parameters before and after collision, which parameters? Naturally velocities. Okay. We use some laws of mechanics, and in this case, because it's perfectly elastic collision and there is no energy dissipation, there is no energy loss, we can use a law of conservation of mechanical energy. So we need to calculate kinetic energy of the system before collision, K1. It is sum of kinetic energy of particles. So it is 1/2 of m1 v1 square, where v1 is a velocity before collision, plus 1/2 of m2 v2 square, where v2 is a velocity of second particle before collision. So this is kinetic energy of the system of particles before collision at this time, at this phase. After that, we can get the kinetic energy of system of particles after the collision. So it's this, 1/2 of m1 v1 with star square, where v1 with star is a velocity of first particle after collision, and the same here. It's a velocity, this is the velocity of a second particle after collision. So this is a shape of first equation when we compare energy of particles before and after collision, because they must be equal. There is no energy lost, and we use law of conservation of mechanical energy. I can remind that if we want to take into consideration also potential energy, it doesn't change because it moves on horizontal line, let's say. Okay, so we don't have to take into consideration the change of potential energy. So we have first equation. For convenience, we can rewrite this equation into this form, where we put out the brackets m1 and we can cancel all halves. So there is m1 by this, and from this side minus v1 star square. And on the right side there remains m2 by this minus m2 by this, and m2 is out of the brackets. Okay, so in this form we can prepare this equation for further calculation. Next, we can use the law of conservation of momentum. Because there is no external force, so then momentum before and after collision are equal. It's very easy equation. This is a sum of momentums of particles before collision. So this is a momentum of system before collision. And this is momentum of system of particles after collision. And we can rewrite it in similar form, putting out of the brackets mass 1, and there remains v1 minus v1 star is equal m2 by v2 star minus from this left side v2. And now it's all about handling with equations, because in fact principal work on this example was done here, preparing two equations for two unknowns, v1 square and v2 square. I can show you how to handle this system quite effectively, so we can rewrite it into this form, first equation, okay, and this second equation is just copied only. And if you can see in this left side, there appeared this term, and we can check it that this term is equal to this term. So this is equal. So if it is equal, so we could substitute this for this, and we get new form of equation 1. So I rewrite this and substitute instead of this by, I continue copying this term, is equal, and I copy right side. Now I can see that I can cancel these terms and this remains only. So this is new form of first equation, and I rewrite also second equation, and I will use it again. Okay, so I divide all equation by m1, and this remain. After that, it's convenient to sum both equations. So if we sum left sides of equations, there will be v1 plus v1, so it is 2 by v1, and v1 star minus v1 star is 0, so it is the only term which remains here, is equal, and I sum these right sides of equation, and I put out the brackets v2 star, so there is 1, and from here there is plus m2 over m1, plus I put out of the brackets v2, and from this equation there remains 1, and from this equation there remains minus m2 over m1. So Finally, I can very easily express V2 star from this equation because V2 star is the only variable in this equation. So this is a final result for V2 star. Finally, I can calculate V1 star, what is from this equation this. And if I substitute for these terms, I can get this result. We can see that it's very similar and the only change is in indices. So there we can observe something like law or principle, exchange of indices. So if we have one result, we can write very easy result for second variable, but we must change indices only. 1 for 2 and 2 for 1. Now I can show you a short analysis of energy balance of this system. So I have shown you already which phases we distinguish on this process, and now I can show you some energy balance of this process. So let's say that there at the beginning we have a kinetic energy K2, and after the process ends, so there is kinetic energy K2, and these energies are equal because there is no energy loss. And what happened here? So because the bodies, let's say bodies, they are considered as particles, but every particle is in fact small body. So for elastic deformation, you can imagine some spring. For deformation of spring, you need some energy. So we deformed, or not we, but bodies deformed by acting of forces, contact forces between M1 and M2. And this deformation needed some energy. So in comparing these two phases, there is some change of energy balance. So between this and this state, we spend some energy, and it's energy loss. And it is energy of working forces. What does it mean that forces are working? So these forces are making deformation. And after that, where deformation disappears and there is some resilience when particles are reshaped to their original shape. So there was also some work of force, the same amount but with plus sign. Okay? And at this point, it means if there is an interim energy loss, it must be loss of kinetic energy. So K1 minus, or I can say it like this. So from this follows that K prime minus K1 must be equal minus VV. Okay? And here I can say that K2 minus K prime must be equal plus VV. Yeah, but it would be better to write it to write it here, okay, because it's between these two faces. So K2 minus K prime is plus VV, okay? So what we lose here for deformation, we get here in a redeforming process. The energy needed for deformation is getting back to the kinetic energy, to the kinetic of the system.